In this lecture, I'd like to talk to you about some other important properties of waves. In the last lecture, we covered characteristics such as the speed of the wave, amplitude, wavelength. So let's talk about some other things in this lecture. Okay, so first of all, let's talk about how waves reflect and transmit. So when a wave strikes an obstacle or it comes to a change in media, right? For example, let's say that there's some light and it's going from air to water, for example. When this happens, at least part of the wave is going to be reflected. If you have a wave reaching the end of its medium and the medium is free to move, then it will be reflected and its reflection will be upright. And that's example B there. But if you have a wave hitting an obstacle that doesn't move, then its reflection will be inverted. And that's shown here in the left in column A. Now, this is an example for waves on a string, right? And this is a common demo that's done in physics classes. But it's worth noting that other types of waves, including light and sound, also reflect and transmit through barriers. So here's some pictures of reflection, for example, for light on the left and sound on the right. And you can see that what happened was the light came to a barrier or a change in medium when it hit the water, and then that caused some reflection, right? And you can see this beautiful reverse image of Mount Hood here in this reflection. Also in sound, right, you have this bat, and it's trying to find prey by sending out these little high-pitched squeaky sounds, and then they reflect off of the prey, shown here as an insect, and bounce back. And that's called echolocation, or reflection of sound waves, and that's how the bat knows where prey is. Of course, bats have terrible vision, so they rely a lot on sound for this sort of thing. Now, also what can happen is transmission. We've all, for example, looked into the water and been able to see things that are in the water underneath. So we know that light isn't just reflected when it goes from air to water or water to air, but it can also be transmitted as well. Okay, so if a wave encounters a denser medium, as shown here, where you have a mass per unit length of the rope that's lighter on the left and then a heavier section on the right, if it encounters a denser medium, then it's going to be partly reflected and partly transmitted. So you'll see a reflected pulse and a transmitted pulse. And if the wave speed is less in the denser medium, then the wavelength is going to be shorter. Now, another thing that can happen with waves is called superposition or interference. So the superposition principle is basically that when two things are in the same place at the same time, then they add up. Okay, and we've seen superposition of vectors, for example, forces on an object will sum to be a net total force, and that's called superposition. Waves do it too. So if two waves pass through the same point, then the displacement of the wave from equilibrium is going to be the sum of the individual displacements. Okay, so we've got two scenarios shown here in the left and the right, columns A and B. So in column A, we see that the displacement from equilibrium is upward on the rope and then downward on the rope. And these two things are moving towards each other. These two different wave pulses are moving towards each other. So what happens here is basically a cancellation effect. When the upward pulse gets to the same place at the downward pulse, they sum together. And since their amplitudes or disturbances from equilibrium are equal magnitude but opposite direction, then the pulses overlap precisely and cancel out, okay? And then once they move on, they continue. So the downward pulse on the rope will continue to travel left. The upward pulse on the rope will continue to travel right. And so they meet, they cancel out, and then they continue on, right? That's called destructive interference. When the amplitude of the summed wave is less than the individual amplitudes of the initial waves, that's destructive interference. Okay, so that's the example on the left. In the right column, or column B, you can see that both of the wave pulses are upwards, okay? And then when they meet at the same point, which is the middle picture here, then the two amplitudes sum to one big amplitude, right, where they get here in the center. And then they continue to move to the left and the right, and they break up again, and you see the small amplitudes again. When two amplitudes are in the same direction and then they sum to make a larger amplitude, that's called constructive interference. So we have destructive interference, which results in a reduction of amplitude, or constructive interference, which results in an addition or a larger amplitude. So here we see the sum of different waves in different scenarios, A, B, and C here, okay? In A, they're adding constructively, okay? Because the peaks and the troughs meet up, and so you get constructive interference. In B, they add destructively, right? Where you have the peak meeting the trough, and that sums to 0. And then in C, they add partially destructively. And so you can see that you have these two waves, and they're a little bit mismatched, right? But not perfectly mismatched. They're not perfectly out of phase. And so what happens then is that you get a smaller wave that's still destructive interference. It's just not perfectly destructive, right? It doesn't sum to 0. So that scenario is also a possibility. Now, because of superposition, if you have a bunch of waves in a confined space, then you get what's called standing waves or resonance. So standing waves occur when both ends of a string or a medium are fixed. And in that case, only waves which are motionless at the ends of the string end up persisting. Okay, so you end up having, for example, constructive and destructive interference. At the end, the perfectly constructive interference will win out. Everything else will eventually sum to 0, right? Now, you might have a little transition time where you have stuff like this going on, right? But eventually, all the things that destructively interfere will sum to 0, leaving only the constructive interference, and then you'll have pretty standing waves that look like this, okay? So in nomenclature or jargon here, what we do is we call things either nodes or antinodes. At the nodes, the amplitude is 0. And at the antinodes, that's where the amplitude goes to the maximum value. So if you look here, you've got different harmonics, okay, for example, and we'll talk more about this later. In this one, you've just got half of a wavelength, okay? And so the antinode is right there in the middle, and the nodes are where the string is fixed, okay? Now, in the second example, you've got a full wavelength here, okay? It goes up and down. So here you have 3 nodes, right? One at either end, and then one dead in the middle, okay? So those are your nodes. And then the antinodes are here and here, okay? Now, it can go further. You can get more nodes and antinodes. Just remember that as you add on, in this example here, you're going to have a node at either end, okay? So here you have 1, 2, 3, 4 nodes, right? And then you have 3 antinodes. Okay, so let's talk about some numbers behind this. This is important for musical instruments like guitars and pianos, for example. Let's say that you have a string and you give it a pluck, right? So where you pluck it and how you pluck it can result in different frequencies and fundamental harmonics. So what do I mean by that? Okay, so the frequencies of standing waves on a string are called the resonant frequencies. And these are also referred to as the fundamental and then its harmonics, okay? So for example, the fundamental is when you just have 1/2 wavelength in here. And then the first overtone, or what we call the second harmonic. So the first harmonic is just 1/2 wavelength, or the fundamental. The first overtone or second harmonic, that's when you have a full wavelength here, okay? And then the second overtone or third harmonic is when you have 1.5 wavelengths or 3 antinodes, okay? Now you can see here that the wavelength for each one of these changes. This is a 1/2 wavelength. So what for the fundamental? So whatever the length of your string is here, that's going to be half the wavelength. And so the wavelength would be equal to, for example, 2L, okay? Now, if you have the first overtone or the second harmonic, then the wavelength would be equal to the length, L, okay? And then for the second overtone or the third harmonic, then the length of the string would be 1.5 wavelengths, okay? So that's how that goes. Now, if you have your first harmonic, that we're going to call a frequency fundamental F1, right? And then the frequencies will go as multiples of the first harmonic as you go out. So the first overtone or second harmonic will be 2 times the fundamental frequency. And the second overtone or the third harmonic will be 3 times the fundamental frequency, and so on and so forth. So here on this next slide, I've put the wavelengths and frequencies of standing waves into an equation. So for, let's call our fundamental n equal to 1. and then the harmonics going up from there, n equal to 1, n equal to 2, n equal to 3, and so on and so forth, okay? So for your first harmonic, the wavelength would be 2L divided by 1, and then for the second harmonic, it would be 2L divided by 2, so on and so forth, right? So when we put that into equation, if we call the harmonic n, then the wavelength would be 2L over n, okay? Now, since we have that relation in between the speed of the wave v equaling lambda f, okay, then that means that we can solve for the frequencies, okay? So the frequencies of the harmonics f sub n would be the speed of the wave divided by its wavelength lambda n. So since lambda n is given as 2L over n, then when we divide by it, we can solve for the frequency and we get n is equal to, or f is equal to nv over 2L, okay? Now, if we call v over 2L the fundamental frequency, f1, then we can see that n times f1 gives us the frequencies of the other harmonics, okay? So here n equals to 1, 2, and so on and so forth. So remember, the fundamentals are when n equal to 1, and the higher harmonics, I should say higher harmonics or overtones are for n greater than 1. Okay, so that's the deal there. Now, of course, I've been talking about this is hugely applicable in music, especially here we've been talking about waves on strings. So that brings to mind pianos and guitars. Okay, so let's talk about pianos for a second. If you press the piano key, then what that happens there is it causes a little hammer to strike a string inside of the piano. And the piano strings have different lengths. So longer strings have longer wavelengths and produce lower pitch sounds. Because V is equal to lambda F. So long wavelengths have smaller frequencies. Higher frequencies means higher pitched notes, and lower frequencies means lower pitched notes, okay? You can also, as you can see here with these little, I guess, sort of screws that the strings attached to, a tuner can come in and tighten or loosen those strings, right? Which changes the tension in the string, which can change the pitch of the note a little bit, okay? So that's what they do sometimes when they tune pianos. Okay, so let's do an example problem here because those are worth a million words, right? Let's say that we have two strings on a musical instrument and they're tuned to play at G and A. And so middle G and middle A have frequencies of 392 hertz, that's G, and 440 hertz, that's A. So what are the frequencies of the first two overtones for those strings, or the second and third harmonics would be another way of putting it. And then question B, if the two strings have the same length and are under the same tension, right? Maybe that we're thinking of a guitar scenario here, for example, then what's the ratio of the masses of those strings? All right, so here we go. Let's do the solution for this. For the G note at 392 hertz, the first two overtones, or the second and third harmonics, are at 2 times 392, right? And that gives you 784 hertz, and 3 times 392, which is 1176 hertz. Following that same logic for the A note, which has its fundamental at 440 hertz, n equal to 2 and 3 correspond to 2 times 440 is 880 hertz, and then 3 times 440 is 1320 hertz. So those would be the second and third harmonics for those two notes. Okay, now to solve for part B, we're going to use the two equations that we have for speed in strings. So first of all, we're going to use the common equation, V is equal to lambda F, which is true for all waves. And then we're also going to go and use the equation for the speed dependent upon the tension in a string. And so that is V is equal to the square root of the force of tension divided by the mass per unit length, or mu, of that string. Now, since these both describe the same speed, then we can set lambda F equal to the square root of the force of tension over mu, okay? And now it's easier mathematically to think about it if we square both sides of that equation. So I'm going to go ahead and do that. And that tells us that lambda F quantity squared is equal to Ft over mu. And this is what we're going to do to solve this problem. Because what it tells us is that the strings are the same length. So that means that the wavelengths for the fundamentals have to be the same, right? It's going to be that half wavelength for whatever the whatever the length of the string is. And that's because you've got standing waves when you pluck a string in a musical instrument. And the next is the tensions are the same. The problem told us that. And then we're asked to find the ratio of the masses, which means we're going to find the ratio of the mass densities, and that will be the same as the ratio of the masses because the lengths are the same, and mu is the mass per unit length, where L is the same. Okay, so let's go through that logic and that math. So I've got the G note here on the left, that's the 392 hertz. And then I've got the A note here on the right, and that's the 440 hertz. We're going to use the same equations for both. So we have the speed squared is lambda F quantity squared, which is FT divided by mu for both. Okay, so plugging in some numbers, wavelength is the same. So I'm just going to call it lambda because we don't know what it is, but we know it's lambda for both. So lambda times 392 hertz quantity squared for the G note is going to equal to the force of tension divided by the mass per unit length for the G note. And then I can say the same thing for the A. Lambda times 440 hertz quantity squared is going to be FT over mu A. Okay, now what we can do is we can put everything that we know changes on the left-hand side, right? And then we can put everything that we know that's going to stay the same between the G and the A on the right-hand side, okay? So the mass per unit length and the frequencies for the G and the A are going to be different, but we know that the tensions are the same because the problem told us. And since the lengths are the same, that means the wavelengths are the same. And the problem told us that, right? So what I can do is rearrange this equation, right? I can do a little cross multiplication. And when I do that, I'm going to take mu G over to the left-hand side of the equation and then move lambda over to the right-hand side of the equation. So when I do that, I get mu G times 392 hertz squared is equal to the force of tension divided by lambda squared. Now, this is going to be the same kind of logic for the A note. So I have mu A times 440 hertz squared is equal to the force of tension divided by lambda squared. Now, if you're having a little bit of trouble doing the algebra here, just go ahead and pause me. And I'm going to say that for any of my videos, if you need a second to make sure that you can keep up with the math, pause the video and work through the math yourself on some scratch paper and then resume when you're with me, okay? But this is true here. Now, since the stuff for the G note, mu G times 392 squared equals the force of tension divided by lambda squared, right? Now, the force of tension is the same and lambda is the same for both the G and the A note. So that means that the left-hand sides of these equations are equal to each other because they're equal to the same right-hand side, right? So that means that we can set mu G times 392 hertz squared equal to mu A times 440 hertz squared, right? And then we can, since we were asked to solve for the ratio of the masses, form a ratio with a little cross multiplication. So that means that I'm going to divide both sides of this equation by mu A, right? And by 392 hertz squared. And then I'll get the ratio that I want. So here I have mu G divided by mu A is equal to 440 hertz squared divided by 392 hertz squared. When I plug 440 squared over 392 squared into my calculator, I get 1.26. And then this is going to equal to the ratio of the mass densities. But since the mass density is the mass per unit length, and the lengths are the same, it's the masses that are different by this amount, right? Because if I did mu G is equal to mg divided by L, and then mu A is equal to ma divided by L, the divided by L's on the top and the bottom of the fraction would then cancel, leaving me 1.26 is equal to the mass of the G divided by the mass of the A string. Okay. All right. So that's an example problem for you, a little tougher than some. Okay. I hope you understood it, and I'll see you in the next lecture.